Welcome to today's laboratory session. In this session, we are going to see the determination of specific resistance of a given coil of wire using Carey Foster's bridge. Before moving on to the apparatus required and how to do this experiment, let us see a little background about this Carey Foster's bridge. Carey Foster's bridge is a modified form of Wheatstone bridge which is used to determine low resistances, as well as it can be used to compare two large resistances. Let us see about Wheatstone bridge. Wheatstone bridge is nothing but it will be having four resistances. This P and Q are equal known resistance, R is a variable resistance, and S is a unknown resistance. And this is a 2-volt battery which is connected to this bridge through a key. When we pass current through the circuit, this P and Q are equal known resistances. When the one side of the bridge, that is the resistance in one side of the bridge, that is P plus R, when it equals to the resistance of the other side of the bridge, that is Q plus S, the bridge is said to be in a balanced condition, and the Gallo meter will show you a null deflection, and there won't be any current that is passing through the circuit. So under this condition, from the theory of Wheatstone bridge, we can say P by Q is equal to R by S, and if we want to determine the unknown resistance S, S by R is equal to Q by P, or we can find S by making some rearrangement. S is equal to R into Q by P. We already know P and Q are known equal resistances which can be substituted, and this R is a variable resistance. So from this formula we can determine the resistance of this unknown coil of wire. Actually, in meter bridge we will be replacing two resistances with a meter length of a bridge wire. Actually, this is the variable resistance, this is our unknown resistance, and this is the length of the meter bridge wire, right? So this is our jockey, this is Gallo meter, and again it is connected to a battery. When battery is switched on, this part of the bridge has to be balanced against this part of the bridge. So for a particular value of R, we'll be fixing a value for R, and the jockey is moved over the meter length of the bridge wire. And whenever this Gallo meter shows zero deflection, what it means is the resistances in this variable resistance box R plus this length of this wire will be equal to the unknown resistance plus the resistance along this part of the wire. So again the formula is R by S is equal to L1 by L2. L1 can be found with R on left side and S on right side, and interchanging the positions of this variable resistance and unknown resistance, we can determine the value of L2. The balancing length L2 can be determined after interchanging the position of S and R. The formula used to find the unknown resistance using a meter bridge is R by S is equal to L1 by L2, or S by R is equal to L2 by L1, and if we want to know the value for this unknown S, S is equal to R into L2 by L1. This is what we call it as a Wheatstone bridge, and this Wheatstone bridge is utilized in the meter bridge to determine the unknown resistance. And this Wheatstone bridge is little modified by Carey Foster, and the bridge was known as Carey Foster's bridge. What he does was he included two resistances here and here so as to make the potential drop along the length of this wire to get decreased, and that increases the accuracy of the unknown resistance value. So let us see about Carey Foster bridge. This is the circuit for a Carey Foster bridge. Here we have the resistance P and Q which are equal and known. This is the variable resistance R, and this is our unknown resistance S. Actually, in Carey Foster bridge we'll be doing two parts. We'll be doing the experiment in two parts. The first part is to determine the resistance of the bridge wire. This is our meter bridge wire. So first we need to find the resistance of this bridge wire. Then after finding the resistance of bridge wire, in the second part we'll be replacing this resistance with unknown resistance, and we'll be determining what is the value of that unknown resistance. So while doing experiment, in the first part, this is our variable fractional resistance, and this will be a simply copper metal strip which is of negligible resistance. And from the theory of Carey Foster's bridge, R minus S, that is the difference in the resistance between these two R and S, will be equal to the difference in the length, balancing length of the wire. And again L1 can be determined with R along left gap and S along right gap. After interchanging the position of R and S, L2 can be determined. So from the theory of Carey Foster bridge, the resistance R minus resistance S is equal to resistance of the bridge wire into L2 minus L1. And since this S is negligible, because already we said it is a copper metal strip with negligible resistance, and hence we can take this S as almost very small, so we can neglect this part. So R is equal to RB into L2 minus L1. Our aim is to determine the resistance of the bridge wire, and so RB is equal to R into R divided by L2 minus L1. So this is the formula to be used in the Carey Foster bridge experiment to determine the resistance of the bridge wire. In the second part, this metal strip S is now replaced with an unknown coil X, right? This metal strip S is now replaced with unknown coil of wire similar to this one. This is a coil of wire. For this coil of wire, we are going to find the specific resistance of the material of this coil of wire, right? So this wire is in the place of this S, that is copper metal strip. We are going to connect this unknown coil, right? I mean the resistance of the coil which is desired to found out. And again the formula here to find unknown resistance is R minus X. In the place of S now we have our unknown resistance X. So R minus X is equal to RB into L2 minus L1. And we need to find the value of unknown resistance. So minus X is equal to, when this R goes to other side, we have minus R plus RB into L2 minus L1. X is equal to, changing the sign over here, X is equal to R minus RB into L2 minus L1, or we can write X equal to R plus, instead of this L2 minus L1, we have taken as L1 minus L2. So this is the second formula to determine the value of unknown resistance using Carey Foster's bridge. Let us see what is the apparatus required for doing this experiment. So this is our battery, and we want to have 4 resistances. This is the resistance P and this is the resistance Q. Both the resistances P and Q were kept at known equal values, that is at 1000. See here, this is into 10. If we put 2 over here, it represents 20 ohms. If I keep it as 0, it represents 0. And here into 1000, I have kept it as 1. So this resistance box gives you a resistance of 1000 ohms. Q should be made equal to P. So I am keeping all the dials corresponding to 10, 100 and 10,000 as 0. And I had taken 1 in the 1000 dial. That means this resistance box will offer a resistance of 1000 ohms. Thus I have made the value of P, that is equal to Q. And this is our fractional resistance box. As you can see here, it is the dial is calibrated in 0.1 ohms. So if I keep it in 6, it means 0.6 ohms. So this is the fractional resistance, that is R. And this is the metal strip I have told you, right? This is the metal strip. This is the metal strip which can be removed, or if we want, we can include it. This is the metal strip. So this is a Gallo meter to see whether the bridge is in balanced condition or not. And this is a high resistance to protect the Gallo meter. And we have a meter bridge here with a meter scale. So while doing connections, the positive of the battery is, before going on to connections, let me tell you how many terminals are available here in the meter bridge. See here, actually this is one end. This is the other end of our meter bridge. So at the right end, I am going to include this metal strip, and on the left end I am going to keep this fractional resistance. we have two more inner gaps. One is here, which is connected to resistance P, and there is one more gap here, which is connected to Q, right? So there are four gaps. This you call it as an outer gap, and similarly we have an outer gap over here. In the two outer gaps, we need to connect R and S. So in the left outer gap, we are connecting this fractional resistance R, and in the right outer gap, we are including this copper metal strip, which is of negligible resistance. And in the two inner gaps, in the left gap, you are connecting a resistance P, and in the right gap, you are connecting a resistance Q. And both the P and Q were kept at 1000 ohms. And here we have one more terminal between this outer gap and inner gap where P is connected. We have one more terminal. This terminal is connected to positive of the battery, right? And here also on the other side, here we have the outer terminal which is connected to a metal strip, and this is the inner terminal which is connected to the resistance box P, and there is one more terminal which is in between the outer gap and inner gap, which is connected to negative of the battery, right? So we do have a central terminal here which is connected to a high resistance, to this high resistance, whose other end is connected to Gallo meter, and the other end of Gallo meter is connected to a pencil jockey, right? This is the connection. Let me tell you once more. We do have four gaps in this meter bridge. In the left outer gap, we are connecting the resistance, fractional resistance R, and in the right outer gap, we are connecting a copper metal strip which is of negligible resistance, and on the left side inner gap, we are connecting the resistance box P, which is kept at 1000 ohms, and in the right inner gap, we are connecting the resistance box Q, which is also kept at 1000 ohms. And from the terminal in between the outer gap and the inner gap on the right side, that terminal was connected to negative of the battery, and a similar terminal on the left side, that is the terminal which is lying in between the outer gap and the inner gap on the left side, this terminal is connected to positive of the battery, right? The center terminal is given to high resistance, whose other end is connected to Gallo meter, and the other end of Gallo meter is connected with a pencil jockey. Before switching on your battery, please check whether your P and Q are made equal to 1000 ohms. After confirming the equal resistances in the box P and Q, switch on the battery. In the battery, this you call it as voltage panel, and this one you call it as current panel. In the voltage panel, check whether 2 volt is coming out of the battery. If not, you can adjust the course, right? If you adjust the course, you can change the value of voltage in the battery, as well as this fine adjustment can be used to do fine tuning, right? So make sure that your battery is giving 2 volts, and you try to keep your jockey at one end of the bridge. You try to press the jockey at one end of the bridge and check the deflection in the Gallo meter. It is showing on to the right extreme. Let us press the jockey on the left end of the bridge, and let us check the deflection in the Gallo meter, which is going to the left extreme. So what it means is, if you press the jockey along 2 ends of the meter bridge, and if the Gallo meter shows opposite deflection, it means your bridge is working properly. Now, let us, for the first part of the experiment, see here, this is the first table. As I have told you already, we have the formula, RB is equal to R divided by LA minus LB, or LA difference LB. Actually, what the formula we have derived is RB is equal to R divided by L2 minus L1. L1 is the balancing length measured with R on the left gap, and L2 is the balancing length measured with R on the right gap. Now, let us keep R on the left gap. See, this is our fractional resistance R, which is kept along the left gap. Now, we need to measure the balancing length. How to measure balancing length? If your galvanometer shows null deflection at a certain point of the wire, that represents balancing length from the left end. And here we have a meter scale that is provided to measure the length of the wire, which gives you null deflection. So you're going to start your measurement from your left end. So you need to use the scale which is starting at the left end. That is, you need to use the upper scale. Now let me press the jockey over here, and we'll check the deflection in the Gallo meter. It is not actually near to 0. So let me slide the jockey on the Gallo meter wire so that the deflection comes to 0. See here, I am keeping the jockey at one end, at the left end. Check the Gallo meter deflection. Now I am sliding the jockey along the right direction towards the right, so that the Gallo meter shows 0 deflection. Right now the Gallo meter is showing 0 deflection. So this length of wire from this end A to this jockey, you call it as balancing length L1. How to find this length? You have to measure the length along the upper scale. Now it is almost equal to 29.9. So now let us write it as 29.9. That is the balancing length L1. Now what you have to do to find L2 for the same resistance in the box 0.6. Now you need to calculate what is the value of R, value of balancing length L2 when you keep the fractional resistance box R in the right gap. So what we have to do is, before going on to take the value of L2, we can change the value of this fractional resistance from 0.6 to 0.7. Now the resistance in the fractional resistance box is 0.7. So I have to take 0.7 on the R column. Now again I need to find what is the balancing length. So keep the jockey from the left end. You need to move the jockey from the left end, and you are not supposed to slide the jockey over the wire, but you need to measure, you need to check the deflection in the Gallo meter by putting the jockey at some point of length of the wire, right? You should not slide on the wire. You should not make the jockey to get slide on the wire. You pick up the jockey, put it at some point of the wire, and check what is the deflection in the Gallo meter, right? Now the deflection in the Gallo meter is decreasing. See, at this point it is going to the right side. I need to have 0 null deflection, so that that represents balancing length. So now it is 0. What it means is the length of the wire up to the point where jockey is kept represents the balancing length L1 for the resistance 0.7. Now check what is the length over here. What is the balancing length now? It is nearly 26.8. Right? Let us write it down. 20. Let me check it up again. The balancing length is, this is the balancing length now, 26.8. Let's write it down. 26.8. Similarly, we can change the resistances in the fractional resistance box to 0.8, 0.9, 1.0, and you can make the Gallo meter to show null deflection by keeping the jockey at different points along the length of the wire, and you can measure what are the balancing lengths. For each resistances, you can measure what are the balancing length, and you can fill it up for 0.8, 0.9 and 1.0. Right? Now what you have to do? Now the positions of R and S were interchanged. Now on the left gap, I have the metal strip. I have included the metal strip, and on the right gap, I had excluded the metal strip and included this fractional resistance, right? In the first part, while filling this column, we have taken R in the left gap and metal strip on the right gap. Now I have replaced, I have interchanged the positions of R and S such that now this fractional resistance R is in the right gap and the metal strip is on the left gap. Again, I have to put 0.6 in the fractional resistance box, and I need to measure the balancing length. Let me take 0.6 on the fractional resistance box R, and let me check the balancing length again. Check the deflection in the Gallo meter. It is to the extreme right. The deflection is decreasing. The deflection is decreasing. It is around 0. Let me check it precisely. So this is, now the deflection in the Gallo meter is 0. Now this represents the balancing length. Again I have to check the upper scale, and this balancing length you call it as L2. Again I have to measure it from that extreme left end, and now this is the balancing length L2 for the same resistance 0.6. Now the value is equal to 68.8. So I need to write it as 68.8. Now what can I do? I can increment the value of this resistance R to 0.7, 0.8, 0.9 and 1.0, and as before I can measure the balancing length L2, and I can fill this column also. Right? How to do this calculation now? I'm sorry, instead of filling the first table, I have filled the second table. Let me take the values here, 29.9, and here it is 68.8. Now how will you do this calculation? RB is equal to R divided by LA difference LB, or from our formula we have written RB is equal to R divided by L2 minus L1. Right? This is the value of L2, this is the value of L1, and this is the value of R. So how will you do your calculation? R is equal to 0.6 ohms divided by L2 minus L1. L2 is 68.8 centimeter. So 68.8 minus L1 is 29.9 centimeter. So 29.9 into 10 power minus 2 meter. Right? Actually these things are in centimeters. So we have to take it as 10 power minus 2 meter in the denominator. We'll take this 10 power minus 2 to the numerator and keep as it is. So we'll be having 10 power 2 this ohm by meter. Right? Let's keep this 10 power 2 as a common value. Let us try to calculate the value for this R divided by L2 minus L1 alone. Right? So what is this R divided by L2 minus L1? Let us do the calculation. 0.6 divided by 68.8 minus 29.9. Close the bracket. So I'm sorry, I have not done divided, I have given minus. So 0.6 divided by 68.8 minus 29.9. So what is the value? 0.0. You can take 4 decimals, 4 numbers after the decimal point. So 0.0154. 0.0154. Right? Similarly, you can do all these things. We have calculated the value of L1 for all the other resistances. Similarly, we have calculated L2 also. We have observed L2 also after interchanging the positions of R and S. Now we can calculate the value for bridge resistance for all these values, and we can add all these values and divide it by 5 to get the mean RB value. Right? You will be getting something like dash point 1, 2, 3, 4. Right? You will be getting a mean RB value, and for doing the second part of this experiment, we need to replace this metal strip. Already we have a metal strip over here. This metal strip should be replaced with the given coil of wire. Right? We have a coil of wire here. We can replace with this with the metal strip with this coil of wire. So for the second part of the experiment, we have this fractional resistance R along the left gap, and I have replaced the metal strip, copper metal strip, with the given coil of wire whose resistance has to be found. Now you switch on the battery, and please check, ensure that the battery is giving out 2 volts, and again keep your jockey at both ends of your meter bridge and ensure that your Gallo meter shows opposite deflection. See, now the deflection is onto the right extreme, and let me keep the jockey on the right extreme of the wire, and let us check the Gallo Meter deflection, which is to the left extreme. So the circuit is still working properly. Now let me keep 0.6 in the fractional resistance box R. The fractional resistance box is kept at 0.6. Now let me check the balancing length over here on the meter bridge. Let me show the deflection in the Gallo meter. Now I am keeping the jockey at different points of wire. Let us check the deflection in the Gallo meter. The deflection in the Gallo meter is now exactly 0. The Gallo meter is now showing 0 deflection. Let me take this length from the end A as balancing length L1. Now as you can see here, the upper scale gives you a value of 43 point something. So let me take it over here. So here the value is, previously the value taken was actually 45.1. So let me take it as 45.1. And now I have to change, as in the previous table 1, I need to change the resistance in the box R, fractional resistance box R, to 0.7, 0.8, 0.9 and 1.0. And a similar procedure can be adopted to find the balancing length L1 with the fractional resistance box R along the left gap. Now to fill this column, second column, we need to interchange the positions of R and the unknown coil of resistance. Now let us, after interchanging the position of this coil of wire and the fractional resistance R, I need to take the fractional resistance to this left extreme, the outer gap of the left extreme, and this coil of wire should be connected to the outer gap of the right extreme. Now again the balancing length can be found as before, and let the balancing length for the resistance of 0.6 in R is equal to 54.8. Similarly, we can change the resistance in the fractional resistance box R to 0.7, 0.8, 0.9 and 1.0, and we can note down what is the balancing lengths. And how will you do the calculation for this unknown resistance X? As we have found out, the equation to find unknown resistance X is R plus RB into L1 minus L2, where L1 is the balancing length with R on the outer gap of the left extreme, and L2 is the balancing length while we keep that fractional resistance R in the right outer gap. And this R is the resistance in the fractional resistance box. This RB represents the resistance of the bridge wire we have calculated in the first part of the experiment. How will we calculate this X? The formula for X is equal to, what is the formula? R plus L1 minus L2 into RB. Now this R is equal to 0.6 ohms. We have kept 0.6 here, so we'll replace R with 0.6 ohms plus the value of L1 is 45.1. You should not replace L1 with L2 and all. The formula says X is equal to R plus L1 minus L2 into RB. Even if the value of L1 is lower, you need to take it at the first value. So L1 is equal to 45.1 and L2 is equal to 54.8. Both were in again centimeters, so we need to write into 10 power minus 2 into the value of RB is taken from the first table. We need to take the mean value of this RB. Since it is not available, let me take the value of RB as 0.0154 into 10 power 2 ohm per meter. Okay. Let me do this here. So 0.0154 into 10 power 2 is ohm per meter, right? And here we have a meter. This meter get cancels with this meter, and this 10 power 2 get cancels with this 10 power minus 2. In units, we have only ohms in the first part and ohms in the second part. So the unit is ohm, and we need to calculate this value, that is 0.6. We need to do a calculation. So 0.6 plus 45.1 minus 54.8 into 0.0154. Let me include another bracket over here. Let me do the calculation again. So we have 0.6 plus, let me open up a bracket, another bracket, 45.1 minus 54.8, close one bracket, into 0.0154, close the other bracket. We'll have the value as 0.45062. We need to take 4 digits after the decimal point. So we have 0.4506. Similarly, we can do calculation for rest of the R values, and again we can add all the 5 values and divide it by 5 to find the mean value. So mean X is equal to dash point dash 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 ohms, right? The unit is ohms since it is resistance. Now our aim is to determine the specific resistance of the given coil of wire. What we have done so far is we have found out what is the value of the unknown resistance. We have not found out the specific resistance. You know, specific resistance is nothing but it is the resistance offered by a conductor of unit length and unit area of cross section. The length of this coil of wire can be got from the manual, or we can get it from the lab technician. And the area of this coil of wire we can found by using the formula pi r square, right? Area can be found by using the formula pi r square, where r represents radius of this coil of wire. How will you find radius? We can find radius using screw gauge, right? Using screw gauge, by keeping this screw gauge at 3 different places on this unknown coil of wire, we can determine the diameter of the wire. From that we can determine radius, and eventually we can find area of the wire, right? So how will you do it? So we need to keep the wire at 3 different places, and we need to observe the pitch scale reading as well as gauge scale coincidence. We need to calculate the observed reading as well as correct reading. If you take mean of these 3 values, it will give you the diameter of the wire, and if you divide that mean diameter by 2, it will give you the mean radius of the wire. How will you calculate area? Area of the wire is equal to pi r square. We have the value of radius here, so if you multiply it with pi and square it, you will be getting the value of A, and we can get the value of L from the lab technician. So what is the formula to find specific resistance? You know, resistance of a wire is directly proportional to length, and it is inversely proportional to area of the wire. And if you introduce a proportionality constant, we have R is equal to rho into L by A. This rho, you call it as specific resistance or sometimes resistivity, which can be found by rearranging this equation. Rho is equal to R into A by L. R represents resistance. Here the resistance of the unknown coil of wire is taken as X, so simply we can substitute X for R, and instead of area we can write pi r square, which can be found from table number 3 using screw gauge, and this is the length of the wire. If you substitute all the values over here, you will be getting what is the value of specific resistance in terms of ohm meter, right? So this is how we can determine the specific resistance of a given coil of wire using a Carey Foster's bridge. Thank you.